Today we're looking at compound events when we're talking about counting things. Okay, so a lot of times what happens is situations have more than one thing happening at a time. Okay, so we've done some of these before when we were just doing permutations and we said that we were having a group of kids standing in a line and some of them were boys and some of them were girls, right? So those were technically compound events because you had kind of more than one thing happening in the problem. Okay, we're going to keep looking at that, but now we're adding in the fact that these are combinations, which makes them a little bit more complicated sometimes. Okay, so the first thing that we're going to look at here, this first problem. So we have this beta club, which is just like a club. Okay, they have 14 male, 16 female members, and we're making a committee. Okay, so we've done problems like this before where it's just been like lining people up where the order mattered. But now we're talking a committee where the order does not matter. Okay, so we're making a committee of 3 men and 4 women. How many ways can this be done? So we're going to start setting this up just like normal, right? I'm choosing 3 men and then 4 women. Okay, and just like normal, I've got 14 choices for the first man and then 13 and then 12. Okay, and then for the women, I've got 16 choices and then 15, 14, 13, right? Because every time you use a person and they join the committee, then that's it. They can't join again. Okay, but now we have to deal with the fact that the order doesn't matter. So we multiply all this together. That's going to give us how many ways it's possible for this to happen when you have 3 men specifically here, here, and here, right? And in a particular order. So what we need to do is we need to get rid of that. We can't divide by 7 factorial here. That might be your first instinct, is that we've got 7 slots, so divide by 7 factorial. But the problem with that is that when you're dividing by a factorial, it's because you're allowing for a change in position. Okay, and in this case, because of the way we set this problem up, these 2 people, for example, couldn't possibly have been chosen in the reverse order because we said specifically that this was a man and specifically this was a woman, right? The people that are allowed in this category aren't allowed in this category. So there's no way, right? If we picked Bob here and Katie here, there's no way it could have been that Katie was picked here and Bob was picked here because Katie wasn't an option in the men. Okay, so I'm not going to divide by 7 factorial. What I'm going to do instead is I'm going to divide by 3 factorial for all the different ways that the men could have been ordered, and by 4 factorial for all the different ways that the woman could be ordered. So I'm going to divide not by 7 factorial, but by 3 factorial, 4 factorial. And again, this one was for the men, right? And this one was for the women. All right, now you may be thinking to yourself, but isn't 3 factorial times 4 factorial, isn't that exactly the same thing? In fact, it is not, right? So 3 factorial means 3 times 2 times 1, right? 4 factorial is 4 times 3 times 2 times 1. 7 factorial is 7 times 5 times 4 times 3 times 2 times 1, right? It's not going to be the same thing, right? Because you got a 7 and a 5 here that you don't have in this guy. So it does make a difference. You can't combine those together. Okay, so then I'm just going to go to my handy dandy calculator. Okay, and we're going to type in, so 14 times 13 times 12 times 16 times 15 times 14 times 13. And then I need to divide this by 3 factorial, 4 factorial. So when you do this, either do divide by 3 factorial and then do another divide by 4 factorial. So you can do it that way, right? Or you could take that answer, that 953971120, and divide it by, and then do parentheses 3 factorial times 4 factorial. Okay, so it's got to be one of these 2 ways. Either divide both of them or put parentheses around them, multiplied, and divide that. All right. Now, personally, as I said before, I kind of recommend that you just sort of memorize the small factorials. Know that 2 factorial is 2, right? 3 factorial is 6, 4 factorial is 24. It'll save you some time because then instead of doing all that factorial business, right, I could have just said, oh, well, I know 3 factorial is 6 and I know 4 factorial is 24, and there's my answer. So it's just a little bit faster. Okay, so that works out to $662,000. All right, great. Let's look at the next one. So this one, we got a candy store. They sell milk and dark chocolate versions of caramels and peanut butter cups and turtles and coconut clusters. Sounds delicious. How many ways can you select 5 different chocolates if you want 2 of them to be dark and then 3 of them to be milk? Okay, so we are selecting 5 chocolates. So I know I need 5 slots because I'm making 5 choices. Okay, I want 2 of them to be dark chocolates. And then I want 3 of them to be milk chocolates. Okay. Now, I'm thinking to myself, does it matter what order these are selected in? No, right? When you go and buy a box of chocolates, right, they usually just throw them all in a bag. If you've ever gone to a candy store and picked out candies, right? They throw them all into a bag and then you got them all mixed together or put them in a box maybe. But it doesn't matter what order you pick them in, you get the same things, right? Okay, so the order doesn't matter. So we know this is going to be a combination. So for our dark chocolate version, so we've got, let's see, there's 1, 2, 3, 4 candies, right? So there's 4 different types of candies that I could have as dark chocolate. Okay. And keyword here, they said they want them to be different. So even though the store would allow me to take the second one to be the same, right? The store would allow me to say I have 4 more options here. But because we've said we want different ones, okay, that is the thing that indicates that there are no repeats. Okay, so that's how we know we can use a combination here. So I'm only going to have 3 options left for a dark chocolate if I want it to be different. Then for the milk chocolates, I'll have 4 options, 3 options, 2 options. Okay, and then just like in the last problem, I need to divide out my order, but I can't divide by 5 factorial because these aren't interchangeable, right? They have totally different categories. So I sort of have to do it in pieces. So I'm going to divide by 2 factorial for the 2 dark ones, and I'm going to divide by 3 factorial for the 3 milk ones. Okay. Handy dandy calculator. So I'm doing 4 times 3 times 4 times 3 times 2. Dividing by 2 factorial is 2. And then I'm dividing by, I know 3 factorial is 6. So that works out to 24. Okay, and again, make sure you do the dividing for both of them. So it's not divided by 2 times 6. Okay, cool. Next one. Choosing a team for a video game. We've got 10 Avengers and 12 X-Men to choose from, and we need to make a team of 6 players. How many different ways can we choose our team if we want to have an equal number of Avengers and X-Men? So we're choosing 6 players and we want an equal number, right? So I'm making 6 choices, so 6 slots, and I want an equal number of Avengers as I have X-Men. Okay, so there's 10 Avengers to choose from. So 10, 9, 8. Right? And then there's 12 X-Men to choose from. So 12, 11, 10. All right, so there's our general setup. Now we're making a team. When you make a team, it doesn't matter who you choose first and who you choose last, right? So we're just forming a team. It's not dodgeball. There's no competition where you got to get the good players first so that the other guy doesn't get it, right? So I'm going to multiply all that out. I'm going to get that answer, and then I need to divide by 3 factorial and another 3 factorial. 3 factorial for the Avengers, 3 factorial for the X-Men. So calculator, 10 times 9 times 8 times 12 times 11 times 10. And then I'm dividing that by, it was 3 factorial twice, and I know 3 factorial is 6. So I divide by 6 twice. So that works out to 26,400. So a lot. You have a lot of different options for your team. All right, last one. A library has 124 books in the sci-fi section, and it's got 36 movies in its Blu-ray collection. You want to borrow 6 items. How many selections can we make if we want 2 of them to be movies? So 6 items. All right. And we want 2 of them to be movies. So I'm going to have 2 movies. And then by default, the other things are all going to have to be books, right? Okay. So my options for movies, there's 36 choices for the first movie. Once you decide on one, you've got 35 choices left for the next one. Books, there's 124, right? And Once you choose one, 123, then 122, then 121. The order doesn't matter, but again, I'm not going to divide by 6 factorial. I have to divide by 2 factorial and then 4 factorial, right? 2 factorial for the 2 movies, 4 factorial for the 2 books. Okay. Calculator. So 36 times 35 times 124 times 123 times 122 times 121. And I'm dividing that by 2 factorial, which I know is 2, and 4 factorial, which I know is 24. So that's a nice big number. 59101888130. Throw some commas in there so I can read this thing. Almost 6 billion different options, right? And like, that's a pretty small library, right? Only 124 books and 36 movies. It's pretty small. Think about like the Derry Public Library and all the different books they have and all the different movies and everything else that they have. Like, they have more than just books and movies, right? So think about how many different selections you could make if you went in there to pick some stuff out. Sounds great, right? It makes you want to go to the library. Okay, so this is compound events, and as you can see, our combinations and permutations are starting to get more complicated. Okay, so again, make sure that you're reading these and that you're really thinking to yourself about whether or not the order matters in these problems. Okay, so take time, really think about each problem. Don't just start doing numbers.